let's pick up from last lecture. Okay. Yeah, so last time we defined lots of definitions, value functions, action value functions, Bellman equation, Bellman optimality equation, and MDP, Markov property, and so on. Okay, so here, if we can assume the model is known, so when I say model is known, we have the transition function available to us and the reward function available. Then we can do policy evaluation. So given some policy pi, we can compute the value of policy, meaning what is the expected value or expected return following, strictly adhering to this policy and starting at some state S. So value of a current state S can be defined by itself. So if we follow the policy pi, we're going to select an action according to the policy. So we take expectation over the policy, and we're going to get an immediate reward at that state, and discounted future reward. So here we have an expectation over the next state of the value of the next state. So we do one-step look ahead, all based. We saw this, so this is all based on Bellman equation, right? V pi. Okay, so so this was given the policy. We can evaluate the value of the policy for all states by this equation. So if we have evaluated all the values for all states, and value of a state is related to the value of the related to the action value, the Q. So it's simply just expectation over the policy of the action value function, right? By definition, and you might think of a natural improvement. So given we have computed this or this, if we do one-step greedy action, so here to select the immediate next action, if we take just insert all possible action here in the queue and take the greedy action, whichever has the highest Q value. So in other words, if we insert definition of Q here by this relation, then the one-step greedy action for a given state is simply just whichever action that has highest sum of immediate reward and discount to future reward. So if we know how good each action is under the policy, then choosing the best one should not make the policy worse. That's the intuition. And here is the formal theorem. So theorem is let pi tilde be greedy with respect to q pi. So this is one-step greedy action. Just looking at immediate next consequence. Then the claim is that value of pi prime for any state is greater than or equal to value of pi. So the consequence is if we select the action that's greedy with respect to q pi, then the value improves. We don't make it worse. Give me 1 second. Okay, so this motivates an algorithm, right? So we start off with some arbitrary policy, some random policy. Given that random policy, we fill in the values for all states. Given the updated values for all the states, we improve the policy by making greedy with respect to the newly computed value functions or values for all states. And given this policy, we now reevaluate the values for all states. Given the updated values, we improve the policy and so on. Okay, so let's look at the proof together. So I changed the proof a little bit, so it's more self-explanatory. Okay, so again, pi prime is greedy with respect to the q value. So q pi evaluated at pi prime, of course, is going to be greater than or equal to taking expectation. Right? This is taking max versus expectation, which right-hand side equals v pi here. And let's expand the left-hand side. So q pi evaluated at pi prime. That's the immediate reward, immediate consequence of executing pi prime, plus discounted expected value onwards, starting from next state s prime. So from these two equations, we have that v pi of s is upper bounded by immediate reward upon executing pi prime, plus discounted future reward, future return for all states. Then the trick is to apply the same inequality for all next state values, this guy. So this must hold for all states. So we're going to apply the same inequality here. Okay? So let's call the next state as double prime. All right, now it's time for us to plug this guy in here. Okay. So this part just copy pasted, and here we have established this inequality, and from that we have immediate reward for the next state upon executing one-step greedy action at the next state s prime, plus double discounted future sum of rewards. So unpack this inequality many times until finite horizon depending on the environment or infinite horizon. And we can equivalently write it as expectation under this new policy pi prime of discounted sum of future rewards, conditioned on the fact that we start at s, which is exactly the definition of v pi prime. So for all states, the value improves. So this is the policy iteration, and like I said, so the algorithm is following. You start off with some random policy. You evaluate the values following the policy for all states. And you improve based on your newly computed values by taking one-step greedy action. And then you repeat. And you stop when policy no longer changes. So we have established the fact that if we repeat this cycle, the values for all states will only get better and better. but we haven't really talked about why this converges to the optimum. So in order to do so, before that, I'm going to give you a lot simpler algorithm. So policy iteration involves policy improvement, policy evaluation, and repeat. Simpler algorithm is just directly coming up with the algorithm from the Bellman optimality equation. So as opposed to having this two-phase algorithm, we're just going to have one-phase monolithic algorithm. And this is called value iteration. So policy iteration had evaluation phase and improvement phase, but value iteration is built directly from Bellman optimality equation. So this subscript here is the iteration index, values for all states. For the next iteration is taking action which has highest number in the right hand side, immediate reward, plus discounted future sum of expected return, coming straight off from the Bellman optimality equation. And when this iteration converges, so we repeat this cycle, updating the values for all states until it converges. And if it converges, at the very last step, we can extract the policy by doing one-step look-ahead. What is the action that has highest immediate reward plus discounted sum of future reward? So the interpretation is value iteration directly solves the Bellman optimality equation. So all that's remaining is to prove that this converges to unique optimal point. Okay. Okay, so before that, let's do one more thing. So this is value iteration, and Q value iteration is similar. So this is also built from Bellman optimality for action values. So Q for all states and all actions for next iteration is the immediate reward plus discounted sum of future Q values for future states and actions. So this kind of update or the algorithm, we're going to write it as this curly B or calligraphic B or P star. So this QK is, so easier way to think about this intuitively is, for now, let's just assume, we don't have to, by the way, but just to make it easier to explain and understand, let's just say we have finite state space and finite action space. Then let's think purely in terms of algorithm. Then this is just nothing but a table, a 2D array, right? So it's an array. We have a Q table. S1, S2. So this is just one-dimensional enumeration. I'm not saying state space is one-dimensional. I'm just saying we're going to enumerate it 1D to keep for bookkeeping. Let's say Sn, A1, A2, Am. So we have in the memory just a 2D array. Just think about it as a NumPy array. Okay, so this is just Python NumPy array, two-dimensional. Columns represent different states. This is enumeration of entire state space and enumeration of entire action space. Okay, so you have this Q table. You pass it through, you apply some operator, which is doing this dynamic programming. And next version of the array is, this is QK and QK plus 1. What is this dynamic programming exactly? For some arbitrary given state and action, you have the immediate reward plus you can only transition to whatever this tells you, right? There may be multiple places that you can transition to. Okay, let me draw it more generally. So we're supposed to look up the Q values for the next state and some optimal action. Okay, let me draw it, sorry, even more generally. Okay, so let's say from S2, you can transition to S4 and S10. Then you look up in S4 which one has the highest Q value among the action axis. So let's say this guy has the highest value. And for S10, which one has highest Q value along the action axis? Look it up. So you're going to take the weighted average of these two values and add in the immediate reward. That's going to be your update for this spot. So that's what I mean by this Bellman update or Bellman operator. So when it converges at the very last step, you can retrieve the optimal policy for all states by looking up for any given state which one has the highest Q value. So the policy is simple table lookup. Once everything is fully computed, you just look up in your table the corresponding state and look at which one has highest action. Let's say this one has highest Q value. That's going to be your optimal policy for that state. Okay, so doesn't have to be final state, final action to prove convergence to optimality, but just to make it easier to explain and understand. Okay, so here, now we're going to prove why this converges to optimal unique stationary point. So we're going to define what's called contraction mapping. So for any metric space and any distance measure, a mapping from some metric space to metric space is a contraction mapping. If there exists gamma from 0 to 1, excluding 1, such that distance between two things, distance between any pair of points, x and y, is smaller after you apply the operator or the mapping B to x and y. So again, if you apply this mapping, if the distance between any pair of points x and y gets smaller, then this operator is called contraction mapping. Why smaller? Because we define gamma, it's less than 1. So take any pair of points x and y in the metric space. If distance between them shrinks after you apply the mapping to x and y, then this mapping is called contraction mapping. And Banach fixed point theorem states contraction mapping has a unique fixed point x star, and if you repeatedly apply this mapping, it converges to x star, the optimum point. Yeah, I don't think we're going to prove this outside the scope, but it's not too difficult to prove it. So, for example, how would you prove it converges to unique stationary point?
There is another optimum point.
Right, so proof by contradiction is easiest. So assume there's another optimum point. But by the property of contraction mapping, if you repeatedly apply, distance between them must shrink. So you have contradiction. So we're going to view this Bellman update as contraction mapping. And if it is a contraction mapping by Banach fixed point theorem, then it converges to optimum point. So we're going to prove that the Bellman operator is a contraction mapping under some metric space, which is any metric space and L infinity norm. So let F be the space of bounded real valued functions over state space and action space. But for you to understand it more easily, you can just think about it as finite state and finite action, and you're fine. So, like I said, you can think about it as Q is just 2D NumPy array, and this operator is just some dynamic programming algorithm that, for a given location in the array, it tells you where to look in the array itself and does some computation to update the value. So that's the definition. So B star of Q is immediate reward, discounted expected next state of optimal Q values for a next state and optimal action. And we're going to define Q star as the fixed point. So once you get there, if you apply the contraction mapping, you're going to stay because it's a fixed point. So we're going to repeat this action value iteration until nothing changes, meaning for all states and actions, if the array doesn't change anything, then we can assume safely it has converged. Okay? So value iteration is just repeated application of this operator on our 2D array. So here's the theorem. We're going to claim Bellman optimality operator is a contraction mapping. So for the metric space, which we define here, bounded real value functions over state space, action space, with L infinity norm, our Bellman operator is indeed a contraction, meaning the L infinity norm difference or L infinity distance between two Q tables. So we have two Q tables, Q1 and Q2. Distance between them will shrink by a factor of gamma once you apply this Bellman optimality. Once you apply this contraction mapping B star. So if this is true, then we prove Bellman operator is a contraction mapping. If it is a contraction mapping by Banach fixed point theorem, it must converge to unique fixed point. So we need to show Bellman operator is a contraction mapping, i.e. distance between the Q tables, any Q tables, will shrink if you apply the Bellman updates. So by definition, a fixed point is unique, because otherwise, if you have two fixed points, you can apply Bellman operator, contraction mapping on both of them, and you have contraction. You have a contradiction. So, okay. So for the proof, you don't have to, but if it's easier, just assume this is just some 2D array, finite state and finite action. So for any state and action pair, let's think about the difference between applying Bellman to two different Q tables, Q1 and Q2. So immediate reward cancels out. RSA cancels out, right? So we have this term, gamma times expectation over next state, difference between the best Q1 value for S prime and best Q2 value for for S prime. Now we're going to take the absolute value. So if you take the absolute value here, and as opposed to taking it from here to here, if I push the absolute value sign inside the expectation, I'm going to introduce an inequality. So this inequality comes from the fact that left-hand side, I use inequality end-to-end, but I push the inequality inside the expectation. And this is also not difficult to prove. Absolute value difference of maximum of two functions is upper bounded by a maximum of absolute value difference of the function. So I'm going to use this inequality here. So let's just look at this term for now. Absolute value difference of max of Q1, max of Q2 is going to be upper bounded by max A prime of function value difference, absolute value of the function value difference. So putting this together, the absolute value difference of applying Bellman to Q1 and Q2 for some SA is going to be upper bounded by discount times expectation of max of A prime of absolute value difference. So I just use inequality to switch this guy. Okay. So let's look at what this is. So here is absolute value difference of Q1 and Q2 for some fixed state S prime, where maximum is taken with respect to A prime. So this is going to be now upper bounded by the L infinity norm between Q1 and Q2. Why is that? Right. So here, you take max over all combination of SNA, but here you're taking max of A prime only, and S prime is fixed. Okay, so let's put this together. So we started off with this left-hand side, right? Here. That's upper bounded by X discount times expectation over next state of this guy, which is again upper bounded by L infinity norm of Q1, Q2. Here, the state disappeared. So we take it outside this summation, and this is just summing out the probability. So it sums to 1. Okay, so for any state and action pair, apply Bellman to Q1 and Q2, it's going to be less than equal to gamma times L infinity norm difference of two Q tables, Q1 and Q2. So if we take max over combination of S and A, that's exactly equal to L infinity norm of Bellman of Q1 minus Bellman of Q2. So we have landed at a conclusion saying under L infinity norm difference, the Bellman update is contraction mapping. So this is between two Q tables. If you apply the Bellman operator, the distance between them will shrink by a factor of gamma. Okay. So if you repeatedly apply this Bellman, it's going to converge to unique fixed point and stay there. So that's why value iteration converges to unique fixed point. Yeah, so it explains why tabular dynamic programming works and converges to optimal action value function. And once this iteration converges, you can retrieve the optimal policy by holding in the memory the Q table for whatever state, just to column-wise argmax in the table, and that's going to be your optimal policy for any state. So in practice, having access to this probability distribution and the reward function is almost impossible. In practice, we only observe the samples. And what's even more difficult is we don't get to observe the full sample. We get to decide what action we're going to take. We're only going to observe the partial information, meaning for this specific action, we're going to observe the sample of next state transition and reward. If we have taken a different action, we don't know what the reward and transition will be. So we only have partial information available. That's what makes RL much more difficult than supervised learning. Once we commit to the decision, it has consequences on which data we're going to collect. And for difficult environments, if you make a critical mistake, you may, for example, fall off the cliff and never get to observe what's around the corner, and something like this will happen. So, summary. Okay, this was supposed to be a single lecture. Okay, so we formalized MDP. It's state space, action space, transition function, reward, initial state distribution, discount, and we define a trajectory, and probability on the trajectory is initial state, action, probability of action, probability of next state, all multiplied together in a probability chain rule. And the clean objective is of a policy is, if you follow the policy, what is the expected discounted sum of future rewards? That's what we want to optimize. we're not directly optimizing this. We're doing it indirectly by relying on Bellman equations. And what we discussed all assumes we know the dynamics and reward, which is the limitation. So here in the next lecture, we're going to relieve that assumption. So we're going to think about how to do everything model-free. So if we have only access to the samples, how do we do value learning? And second component is if the state space is, for example, continuous or very high dimensional, it becomes impractical to build the Q table in the memory. So for example, if the state is image, then you cannot hold all possible combinations of the image, right? Because, for example, if you have 256 by 256 image for U into 8 type image, then you have, for one pixel, you have 256 possible values. So your state space is 256 raised to power of 256 times 256. So it's impossible to hold everything in the memory. So if you have high dimensional state space or continuous state space, then tabular RL is impossible. So that's why we're going to introduce function approximators to represent the state. Okay, so the focus of today's lecture is to relieve this model assumption and introduce model-free prediction, control, and eventually lead to function approximators. So the big running theme in this lecture is model-based versus model-free. In model-based RL, you assume access to state transition function and reward function. And the assumption was you can do a one-step look ahead. If we would have taken some action A, what would be the next state and value associated with the next state? So this look ahead is only possible if you have access to this function and this function. And if we do, then we can do policy evaluation, policy iteration, or value iteration to solve it optimally. But in practice, you never know the dynamics or the reward. You only have samples. Just to be super realistic, you don't even know, you don't even have samples for the reward. It's up to you to design the reward. And so is the state. Nobody defines the states for you. You are supposed to design the state vector yourself. And it has huge consequences. You have to design your state space in such a way that the Markov property holds. That's one thing. And you have to do it in such a way that think about what the policy does. The input to the policy is a state, and it's supposed to output the optimal action. So you have to provide sufficient information to the state so that determining the optimal next action is possible. Okay, so we talked about this before. So there's prediction and control. In prediction, you're given a policy, and you're supposed to evaluate or estimate the value associated with that policy. So if I follow this policy at some state S, what is the expected return? And control is how do you find a good or optimal policy? And we talked about value policy iteration in the previous lecture. So just to reiterate the notation, So lowercase r is for the immediate reward at that time step t. And gt, some papers use a notation rt for return, starting from time step t, immediate reward, next reward, next reward, etc. And so for finite horizon, you might have some ending, and this could be timeout, or there are certain terminal states that you go to, and the episode ends. Or you might have infinite horizon where it just repeats endlessly. And the definition of value function, the v pi, is expectation of pi. So following this policy pi, and starting from state S, what is my expected return? That was definition. So in model-free prediction, the goal is to estimate this expectation from sample trajectories. So what is the obvious idea here? If we have only access to the samples, then we cannot apply value iteration because we don't have the transition function. What's the obvious algorithm? Looking at this definition. Right, so we can do Monte Carlo sampling. So starting at some state, we follow the policy until the end, until the horizon runs out, and we just compute discounted sum of rewards, and that's going to be your estimate of the return. So starting at some state, follow the policy until the end, compute this discount sum of reward, that's your estimate. So you can train a network. Sorry, that comes later. So you can do some updates so that you directly compute the sample mean and average them. That's the most obvious idea. So here is the algorithm, Monte Carlo policy evaluation. So it uses complete sample episodes. So suppose you observe a trajectory starting at some state at 0, execute A0 coming from some policy pi, and get some reward. Next state is determined from the dynamics, and so on. So for every visited states, you can compute the actual return. So once you compute this sample return, you update the values for that state. You can think about it as some form of learning rate. The sample return minus the current estimate of the value. So in terms of algorithm, if you observe one trajectory, you can update the values for all states. Right? Not just this guy. So for this, the regression target will be sum of all the future rewards here. And for V of S1, the regression target will be sum of all the future rewards that happen after S1. And so on. So any states along the trajectory can be updated. Right? So if in terms of implementation, you'd update it backwards. You update the last guy, compute the return to go. here, update the state, recompute or return to go, update the state, and so on. So every visit state S, you collect the returns, and the Monte Carlo estimate is, you can do averaging, or you can do some algorithm like gradient descent style with some learning rate. There are many variants. Simplest thing is just to do running average, so or incremental mean update. Just fancy word for running average. Or if you prefer, you can introduce some learning rate and do gradient descent style updates. One of the downside of Monte Carlo method is this only works if you have episodic environment, meaning the horizon is finite. If you have infinite horizon case, for example, some Atari games, it doesn't have a time limit. It just goes on and on forever. In that case, this is not viable because you're supposed to collect the trajectory until the end so that you can exactly compute the return. Because if it goes on infinite times, then you need to you cannot compute the regression target. So TD learning utilizes the Bellman relation. So the definition of value of a policy starting at some state ST is expectation of the policy of immediate reward discounted future expected return starting at ST. So value of some state is related to the value of the next state. So given one sample transition, we can immediately invoke Bellman consistency. So if the value function is correctly estimated, it must satisfy this recursive relation that relates value of one state with respect to value of the next state. So your TD target, or the regression target, will be immediate reward plus discounted value of the next state. So that's this is your regression target, and that's your update. So this is TD learning. To be precise, this is called TD0 because we use one-step transition. You don't have to. You can do TD lambda or TD1 where you use multi-step. Transitions, etc. for your TD target. So your target is immediate reward that happened in this transition plus value of the next state. So your TD error is target minus your current estimate. And your update is you want to update the current belief about the state, value of the state, with some learning rate and the error. So this type of algorithm is called bootstrapping, where you update your guess towards another guess. This is another guess because it involves a value for some other state. So what's nice about this is it utilizes Bellman consistency, and you can learn from single sample. Okay, to contrast these, Monte Carlo, the target here, regression target is the definition, which is discounted sum of rewards And in TD, your one-step predicted value of the next state. So why is this more accurate than V of ST? I mean, it involves V in the target and your current estimate. So one can think both are equally wrong, but why is this more accurate than value of the state? Because if this target is garbage, then you only hurt by doing this iteration. Right, so why is this more accurate estimate than this guy? It's because it reflects upon one step reality. What I mean by that is we got to observe from ST, we executed AT and got RT as a reward and transitioned to ST plus 1. So we got to observe RT and we got to observe ST plus 1. So it reflects upon, it's one step closer to the reality. It reflects upon if you start at ST, execute some action, okay, I get this specific reward and I get transition to ST plus 1. So which state to transition and which reward to get, that's encoded in this TD target. So one step closer to reality is your TD target compared to your prediction. Okay, so Monte Carlo, you need a complete episode. So it only works for finite horizon environment, but TD, you don't need to have finite horizon environment. But in practice, is this technically true? If you use high discount, even if you have infinite horizon, it's going to taper off. Okay, so after I don't know, 1,000, 10,000 iterations, it's going to only add marginally to the return. So you can pretty much ignore the effects that come later. Anyways, so TD learning can learn online. As you receive some sample, you can immediately update your values. But Monte Carlo, you need to wait until you can compute the return by hitting the horizon. And for bias variance, I'm only going to briefly mention Monte Carlo has lower bias in the return estimate of return and higher variance, and TD learning has high bias and lower variance. But at the end of the day, the update formula is you update your estimate, doing some gradient descent style update where you have some learning rate, your target and estimate, and the target is sample return versus one step look ahead from Bellman equation. So we talked about prediction task. How about control? So previously in model-based RL, to retrieve the policy, we had to do one step look ahead. you want to choose the action that has highest sum of immediate reward plus discounted expected future reward, but we don't have access to these guys. So if we could learn the action values, then it would be possible to select the greedy action. So if this was accessible to us, for any state, we could just take the one with the highest Q value. So if we have Q, we naturally have policy. So from these experience or data, how do we learn this Q? That's the framework we're going to think about. Because if we have Q, we immediately have this greedy policy. And further, for practical purposes, we're going to employ epsilon greedy policy. So I'll explain what it is first before intuition. So when we choose an action, with probability epsilon, we're going to select a random action. And with probability 1 minus epsilon, we're going to act greedy with respect to Q. So the larger epsilon is, it encourages more exploration. And the smaller epsilon is more exploitation. So in RL, this is called exploration versus exploitation trade-off. And during training, often epsilon is gradually annealed. It starts off with large epsilon to encourage exploration and decays naturally. So this is a good idea because in the beginning, Q value is going to be garbage. So acting greedily with Q is not going to give you much better data set. So you might as well just do random exploration. So the way I learned it in graduate school was following. So you come to a campus and you say you're a freshman, okay? You just arrived to campus. And there are many restaurants within the campus for lunch, many options available. And say you only have eaten Korean food all your life until high school. And your Q values for Korean food is very high relative to all others because you are very risk averse. You don't want to try other cuisines like Thai food or I don't know, French food or Italian or whatever, Japanese, Chinese, whatever. So without epsilon greedy, you'll only eat Korean food the rest of your life. So this encourages exploration. So you must act randomly if coin flips with probability epsilon. So you must try Thai food at some point. You must try Japanese food or Chinese, Italian, whatever. And you might not like some of them. You might enjoy, I don't know, Japanese better than Korean or whatever. So you give yourself a chance to update your Q values. So in the beginning, especially when Q values are garbage, it's better to explore rather than exploit. But once you have explored enough state space and your Q estimates are correctly calibrated, then it makes sense to dial down on epsilon and do more exploitation. Another example is, say you have a 2D grid, and here is your goal, where if you arrive here, you get plus 10. And you start here. Here's your goal. You have time limit. And let's say you have an area here where you get +1. Then without exploration, you're going to act randomly, and if you hit here, you're never going to escape. You're going to get stuck at this point. So you can only get here. So from any other points here, you get zero reward. How do you get to here? You never know until you do random exploration and eventually get there. You are never going to get here by following Q values. So is random the optimal way to explore? Actually, no. You want to encourage diversity. You don't want to visit the same state over and over. So you want to try diverse state space. So to make it easier to explain, I said random, but there are more sophisticated ways to based on statistics like UCB, upper confidence bound, or something like this. So, all right, so that's the motivation for epsilon greedy. And I'm going to give you two algorithms, SARSA and Q-learning. So SARSA, I'm going to explain what this means in a couple of slides. So SARSA is an on-policy control algorithm. So the name comes from this sample tuple, state, action, reward, next state, next action, SARSA. So here, the target is the Q value target, immediate reward, plus Q value of next state and next action. And the policy is, and the action is sampled from some policy. So policy is fixed. So here's an update. You're going to update the Q value for this specific state and action with some learning rate of SARSA target plus a minus your prediction of the current state and action. So what I mean by on policy, it learns from the value of policy that is actually being followed. So here, we collect the data by following the policy pi, which is given, policy phi. So if you update your values based on the given policy, then this is called on-policy algorithm. In Q-learning, is an off-policy algorithm because I'll explain the algorithm first. So Q-learning approximates the Bellman optimality equation. So the Q target here is immediate reward, discount times one-step greedy action selected according to the Q table. So here's your target, immediate reward, discount, Q value of the next state, and optimal next action. So this is off-policy algorithm because you're updating Q based on some action that you did not actually execute. In SARSA, you update your policy based on what you actually executed, but here you're updating your Q based on something that you didn't actually execute. So here, you can do epsilon greedy Q-learning as well. So you flip a coin with probability epsilon, you act randomly with probability 1 minus epsilon, you act greedily with respect to the Q value. So to contrast the two, so we're going to come back to Q-learning and make a deep learning version out of it. So you may as well just make yourself familiar with this equation. So to contrast, the target is different. So SARSA, you strictly adhere to the policy, and your Q target, you're supposed to use the actual action that you took. But here, you're going to take the max for the next state as t plus 1, according to the current estimate of the Q. We're going to come back to Q-learning in a couple of slides. I'm not sure if we're going to cover this today. Okay, so let's put this into a perspective. So we have talked about model-free RL methods, where estimate is some update amount or learning rate of target minus the estimate. In Monte Carlo method, we actually computed the sample return. In TD0, we used consistency relating the value of current state with next state. SARSA, it's reward plus discount Q of state and action that was followed. So this estimates Q of pi, and this tries to estimate Q of star. So choice of the target determines the algorithm, and the update formula is more or less the same. Okay, so how many slides do I have left? A lot. Many, many slides. Okay, let's go as far as we can. So I mentioned this briefly. So up to now, we said Q is a table. It's just 2D table of all states, all actions. But realistically, this is impossible in real life when state space is very large or continuous even. So high dimensional image, we have exponential number of entries. When it's continuous, we have infinite dimensions. And also, this is a different point. We need generalization across similar states, because it's going to be impossible for us to encounter every state action combination ever, because there are so many states, so it's impossible to encounter every single combination in the state and action space, because this is the size of this is infinite. So we need some way to generalize so that Q estimated from, I don't know, S1, A1 is similar to Q of S2, A2. If S1, S2 is similar, A1 and A2 is similar. Why? Because we cannot visit every single state in action. So in mathematics, there's a well-established notion of bisimulation. So intuitively, it sounds easy. So how do you mathematically define what's similar in RL context? So two states are similar, S1 similar to S2. If next state is similar, reward is similar, so this is recursively defined. So if you're interested, look up bisimulation. Anyways, we need to do something about this. So this is a different issue. So what we're going to do is, as opposed to having a table, we're going to use a neural network. So input to the neural network is state, action, and it's going to output a real number, outputting your prediction of the queue for that state and action. So neural networks are great at this kind of generalization. If inputs are similar, it outputs more or less similar outputs. So DQN is a neural network approximation to the optimal Q function. So this is the neural network parameter. And implementation-wise, for discrete actions, to make it easier, it just takes as input the state only. And it outputs the Q values for all actions, for discrete actions. So as opposed to inputting all actions, it just only takes in the state as input. Then, once you finish training, you act greedily. So you insert image state or some state. You have all the Q values for all actions. You simply need to take the one with the highest estimated Q value. And possibly you can also use epsilon greedy. Okay, so there are many practical headaches that you need to think about when you actually implement this. But unfortunately, we are out of time, so we'll pick it up in the next lecture. Thanks.